Hi, everybody.
Morning.
Good morning. Thank you for coming out here on the last day at 8:30 in the morning. We really appreciate you getting out of bed for us. My name is Ian Coldwater.
And I'm Brad Giesemann.
And we attack Kubernetes. We're here at our talk Advanced Persistence Threats to talk about the evolution of the Kubernetes project and its attack surface, and to look into the future of what evolving attacks on Kubernetes can look like.
And to make things fun, we'd like to show you a few.
Before we start, maybe we'll wait for the extra 30 seconds and ask this very slowly while people file in. We have some questions for you.
By a show of hands, who has some familiarity with containers? Whoa.
Sweet. Who has some familiarity with Kubernetes?
Excellent.
Awesome.
And who's running or looking to run Kubernetes in their organization? Fantastic.
Nice. Okay. That's awesome. Thank you. All right, let's get started. So the name Kubernetes comes from a Greek word meaning helmsman or pilot. It's the same root word we get the word cybernetics from. So on some level, all cybersecurity is Kubernetes security. But what is Kubernetes anyway? Is it this?
Or is it this?
Well, really, it's both. And it's more than that. Kubernetes turned 5 years old last year. It has a strong community, and it's part of a larger cloud-native ecosystem. Both of us have been working with Kubernetes for a few years now. And we've watched the project and its rapid rate of adoption, growth, and change over time. We as attackers have grown along with it. When we first started learning Kubernetes, it was easier to understand the whole stack. This diagram was the first Kubernetes architecture diagram from 2014, before the project went public. Even back then, it wasn't entirely accurate. Up here, where it says firewall, well, the person who made that diagram now describes the authorization on this diagram as aspirational, because in fact, there was no authorization on there at all at the time. Kubernetes has grown a lot since then. And while it still isn't secure by default, it has a much stronger security posture than it used to. As in some, not none at all.
We learned Kubernetes back when things were simpler and possible to understand kind of enough of everything. But newcomers now have a much steeper hill to climb.
Kubernetes architecture now looks like this. In some ways, it works very differently than it did in the last one. And in a lot of other ways, it works pretty much the same. One thing remains consistent. Kubernetes has a lot of moving parts. Here's an overview of the most relevant components in Kubernetes architecture for our nefarious purposes.
So I'll draw your attention to the API server. That's in the upper left of your diagram. It's the front end for the Kubernetes control plane and exposes the Kubernetes API to users and system components. So it's actually a really juicy target because it's the main way to get to etcd. etcd is the key value store where all cluster state is stored and all the secrets. The worker nodes you'll see on the right are where pods and workloads run. And pods are basically just a group of containers that share similar storage, network, and specification for how they're supposed to run. They run on the nodes. And the nodes are controlled by the kubelet and kube proxy. The kubelet manages the life cycle of those pods, and the kube proxy is responsible for getting traffic in and out of those pods. Ideally, though, we're looking to gain privileged access to that API server, or even direct access to etcd, to be able to see all the secrets and maybe see or modify the cluster state. But it's also useful to be able to gain access to the kubelet API on the nodes.
Because Kubernetes is a loosely coupled distributed system, we can not only read secrets and sensitive data from etcd, we can manipulate the state of the cluster by writing to it. So Kubernetes is rapidly growing and evolving. And it's not just Kubernetes anymore. Confused? It's not just you. This cursed image is the Cloud Native Computing Foundation landscape. So overwhelming that even this screenshot from their webpage asks if you're overwhelmed on the top. Every single one of those tiny pictures is a product logo. It's a lot for everyone to keep track of, even for people who often work with and pay attention to this stuff.
A few years ago, Kubernetes was the platform. And now it's a platform for building platforms and part of a much larger cloud-native ecosystem, as you can see. So additional features, plugins, and configuration on top of Kubernetes add whole layers of complexity. And these have to be kept up with and secured independently and together, and they don't always play nice with each other.
As new features have been added, more security features have also become available, and this means that we have many more features to secure. As infrastructure as code enables organizations to efficiently create many clusters with bigger workloads, that means we have more clusters and more workloads to secure. And as infrastructure as code is now capable of automatically generating entirely different infrastructure, sometimes outside of the cluster, it's hard to be able to see that and to be able to keep track of what assets you have in your environment.
So as complexity grows, defenders and operators have a much harder time understanding the aspects of each component and their interactions within the environment. With more moving parts, there's more to configure, there's more complexity per part, and they're more likely to be misconfigured.
Kubernetes has grown really fast, and with wider adoption, the likelihood for malicious activity increases overall. With more organizations using Kubernetes and more people working on them, there's more likelihood for insider threats because there's more hands in more clusters. Even if you're following the principle of least privilege, often somebody has to get it. As Kubernetes adoption grows, it gets more attention from everybody, attackers too. And the kind of security by obscurity strategy that worked in the beginning for Kubernetes when nobody had heard of it and nobody knew how to use it isn't really working so well anymore. Now people are paying attention and they're looking, so everybody has to level up. And as Kubernetes evolves, attackers have to evolve with it. As the project has implemented more security, attackers have to learn more about Kubernetes to be effective than they used to. You used to be able to, I am not making this up, execute commands as root with an unauthenticated curl call into a Kubernetes cluster. You can't do that anymore. Now you need a deeper understanding of the moving parts on the high level, and often a deeper understanding of the Linux primitives understanding the low levels in order to be good at what you do as an attacker. But this need to level up isn't a situation that's unique to attackers. With the pace that Kubernetes moves and changes, everybody needs to level up.
Kubernetes is a fast-paced project. New versions are released about every 90 days, and the support for fixes and security fixes are only applicable to the most recent 3 versions. That means a given version is only supported for approximately 9 months. Features and fixes come fast, and everyone's in the same boat. This means attackers, defenders, and vendors, and everyone in the ecosystem has to move at this rapid speed, and everyone's forced to adjust to this cadence. So due to that rapid cadence, managed Kubernetes providers typically only support versions that are 1 or more minor versions behind latest. For example, the latest generally available Kubernetes release is 1.17, but many are running 1.14 or maybe 1.15 in production because those are the latest versions available to them. This also applies to organizations managing their own Kubernetes clusters, as it always takes some time to test and validate those new releases before they make it to production. But that can actually work to our benefit. We can use this time to look at the new features now, before they're actually used in a few months.
So we've set up the problem set a bit. Everything is complex and only growing more so, and growing at a rapid pace. We all have to level up, and that's hard, but it's doable. We'd like to help you do that. So let's look ahead a bit. What does the landscape look like coming down the pike? What might attackers be able to do going forward? And what do defenders need to know? We'd like to demonstrate some novel attacks to show you some examples of what sophisticated attackers who know Kubernetes well could be capable of. We're pretty excited about them. We hope you will be too. So first, let's get into an attacker mindset. What might an attacker, such as this one, bent on foul play, generally want to do in Kubernetes?
First, you want to compromise the cluster and attempt to gain access as the cluster administrator, the highest privilege you can get. Then you might want to extract the secrets now, and then also as they're being created to maintain that access, and potentially use them to leverage access elsewhere outside the cluster. We probably want to minimize presence in the audit logs from the API server, and we might even want to disable or bypass security policies or logging the API server altogether. But I think more fun would be to run workloads on the underlying Kubernetes nodes to establish persistence and stay out of view of the Kubernetes layer.
Different attackers have different goals and motivations. Cluster admin isn't always the end goal. For folks like insider threats or malicious administrators, maybe they already have it, and maybe they want more than that. It's also important to remember that the cluster itself isn't always the end goal. Secrets don't just exist for the cluster. secrets can also exist in the form of cloud metadata, and some attackers are looking to move laterally outward into cloud accounts. So, first demo. Let's say that we are a malicious administrator, or otherwise an attacker who has already gotten cluster admin. We have access to all the data and secrets in the cluster right now, but you never know, things might change. So it would be nice to see what's going on in real time. What if there was a not so obvious ways of getting copies of the most sensitive items in the cluster in real time as they're created or updated? Everything flows through the API server before it gets saved to etcd. So what if we had the ability to stealthily spy on the traffic and make sure that we get every secret as they get made or updated? What if we could do that using one of Kubernetes' native capabilities? That'd be pretty sweet, right? So there is a component of the API server that we can misuse for this purpose. It's a form of admission control, often used to enforce security policy, and it's called a validating webhook. A validating webhook is a native configuration option that lets a cluster administrator check with an external web service for whether or not to allow a resource to get created. If you've heard of things such as Open Policy Agent, Gatekeeper, or the KRail project, they use this mechanism for enforcing security policy. Here's how it works. When a user submits a request to do something like create a new pod, after going through authentication and authorization, it gets to the validating admission controllers. If a validating webhook is configured, a full copy of the pod request is sent. The admission controller can then parse the request and use custom logic defined by configuration as code to say yes or no to the request. If the logic allows it by sending a yes response, the pod can be saved in etcd, and it gets created. You can have multiple validating webhooks in a configuration if you want to, and you can pick which resources you want to trigger on. And the best part for our purposes is that custom web service doesn't have to run inside the cluster. It can run anywhere, like to an arbitrary URL on a system somewhere else.
As an attacker or a malicious admin, you might want to create a webhook that's called only when secrets are created or updated. You can install a webhook like this, filter only on secrets, and send it to an attacking system that just logs what it receives. So revisiting this data flow, but with our malicious webhook in line on the right side there, so we can, maybe sometime later, a user goes and creates a new secret via the API. Again, that's step 1. And we'll assume it gets accepted by the first validating webhook in steps 2 and 3. In step 4, though, the entire secret gets sent to the attacker-controlled application via web request. We can configure our malicious application to log the secret and always just say yes and approve the response. And then it gets saved in etcd as normal. But being good evil attackers, we don't want them to notice if our custom webhook service is down. So we can tell the API server to wait just one more second for our web service to respond yes. But if we don't respond, tell it to fail open and just accept it anyway like we weren't even there. So at best, we add a few tens of milliseconds to this request workflow, and at worst, we only add 1 second. Not really enough to notice. So we'd like to show you a demo. All right.
That is not currently being seen.
There we go.
Okay.
So let's assume we have compromised the cluster and have cluster administrator access. I'm just going to show you. We have 2 nodes in this cluster. We have a control plane node and a worker node. And as you can see, it's pretty basic. There's not much running in here. It's pretty stock.
We're using something called kind, which is an easy way to set up a Kubernetes cluster.
And the default secret in the default namespace is there. So nothing really user-created just yet. So validating webhooks require a valid TLS key pair. So we can generate that and insert it inside the cluster. Okay, so we've created a CSR and made a key pair, and we've stored it as a secret called validator. There it is. So that's the validator secret. We're going to use this in a second. So we're going to actually export it out because it was automatically generated with a kube control get secret validator, and we're just going to use JQ to help us get it to a file called cert.pem. So So now we're going to install our malicious application, ready to accept the secrets and log them, and respond yes at all times. So we're going to kubectl apply validator.yaml. So we've created a config map that holds its configuration. We created a service to help find validator inside the cluster. And we've created the deployment where our malicious application is running. Now, we're running this inside the cluster here, but we can very easily use your imagination and put it anywhere you want. And I just want to call your attention to a couple key settings here. So validator is where the webhook is being sent. The failure policy is ignore. So if you don't get a response from us, just ignore that. That's fine. Timeout is 1 second. And as you can see down here, these are what we're talking about, what we're triggering on. So we have, anytime there's a create, update, or delete to resources named secrets. As you can see, we were testing with everything. So we left that in there so you can see what that would look like to get everything. So now we're going to install the validating webhook configuration. This is telling the API server to send all secret requests to our application. So kubectl apply. And really, the only thing an administrator might notice later, if they're not really looking at their logs, is if they run this command, they might see this. But we can call this something like security enforcer, something that blends in, maybe even OPA or Gatekeeper or KRail. Somebody might just assume that security was added. Oh, I'll leave that alone. So now some time has passed, and a new user comes along and wants to create a secret. So we're going to kubectl create a secret named honk from the string key value honk RSA 2020. Now, the damage has been done. That was it. You notice the secret, nobody noticed anything. It just looks like, yep, took my secret. But if we go over to our application and we run the logs on our app, we can see in the web request right here, and remember, that's just base 64 encoded. That's pretty easy to decode. Honk RSA 2020. So we had that whole secret specification in the clear sent to us, and nobody really saw it. So now we have a permanent method for ensuring we're always aware of the latest credentials and secrets stored in the cluster in real time.
Yeah, okay, that was pretty cool, but it leaves trails. Administrators who are looking can still see it if they know where to look. So let's improve on that. In some managed Kubernetes providers, you can't control certain aspects of a cluster for security and stability reasons. Without an ODay of the API server, there's not necessarily much you can do in there, at least directly. In the case of GKE, which is Google Cloud Platform's managed Kubernetes offering, this means that there's no access to the control plane nodes or their auditing configuration. At least, so GKE thinks. GCP's logging system is called Stackdriver, and all GKE's clusters send API server audit logs to it automatically. Anytime an auditable log happens in the API server, or an auditable event, a full log is sent off for viewing, troubleshooting, and analysis. It says who did what and when, and includes the full payload of the requested action. This is great, right? For defenders anyway. Attackers can't do anything without being seen. And they can't prevent their actions from being seen at all. Or can they?
So knowing that the maximum size of a request to the Kubernetes API is just over a megabyte, but the maximum log field size that Stackdriver will parse is much smaller, we can actually prevent the audit logs from seeing the contents of our activities. So if every request we make is large enough, we can pad the requests such that, using fields like annotation, such that the request is long enough, but it still behaves just like we want.
So if we pad the request enough, people can see that the request was made, but they'll only be able to see the metadata in the request. They won't be able to see anything on the bottom, such as anything we might not want them to see. One of the ways to do that, as Brad said, is to pad a request using certain fields like annotations, which are like labels, with really long strings.
So here's a Stackdriver log of a normal request to create a pod named mypod. And the full request body includes the entire pod specification. If anything suspicious was in there, like Ian said, mounting root, running as root, or mounting the host file system, or running as privileged, it would easily be detected, especially by humans or machine. But what if we try to create myPod2 with an oversized request? The log parsing system gives up, and it only records the metadata. We haven't hidden the fact that a pod was created, but now it's no longer possible to see the pod's actual configuration. So let's see an example of what those requests look like. Forgive me. Okay. So we're going to show you a regular size request and an oversized request to create a new pod, named oversized and regular. So looking at the regular YAML, this is probably the smallest possible pod configuration that makes sense, right? We can make my pod with the image Nginx.
Pretty standard.
But this is the oversized pod called myPod2. And as you can see, we have an annotation called A1, and we have some padding.
What is this data anyway?
I got it from Lorem Ipsum, and then I base64 encoded it, just several hundred paragraphs worth.
So it's like endlessly scrolling nonsense, like Twitter.
Still going.
It'll keep going for a while. Infinitely scrolling, endless nonsense.
You know what? Sorry, we'll just skip that. We'll go this way. We'll go this way.
So after that, like when the Stackdriver sees that, all they'll be able to see is that annotation. They won't actually be able to see anything interesting that we did on the bottom that might have manipulated the control plane node. Useful for us as attackers. And that's cool. But all that bypassing of controls and logging is kind of a lot of work. The real API server, with all of its authentication, authorization, validation, and audit logging, is annoying for us as attackers to have to use. If we use it, our activity gets logged, and we have to conform to its security policy, or make live changes to bypass it, such as the one we just demonstrated, that admins or developers might notice. And that's a bummer. So what if we could avoid it? In some clusters, you can schedule pods on the same nodes as where the API server runs. Assuming that your cluster admit, this also means that you can access the TLS keys and credentials that are necessary for the API server to be able to communicate with etcd, which are typically stored on the file system of the control plane nodes. And running a pod on the same node as the API server almost guarantees you network access to etcd. With our own access to etcd, we control everything in the cluster. And depending on what kind of metadata is stored in etcd, we might be able to control cloud accounts outside of the cluster too.
So what if we scheduled our own replica of the real API server to run on the same node and use the same keys and network path to access to etcd? But instead of logging and blocking, we just allow full access. And as an attacker, that's pretty nice. It keeps the logs of the real API server clean and maintains a persistent access channel to the underlying state of the cluster where all the loot is kept. So let's demonstrate. Always going to the wrong one. Clear.
Not quite there yet. There we go.
So we've already made an exact copy of the current API server configuration, but we've made a few key changes. Let me show you those. I want to call your attention to these four right here. We're turning on allow privilege, that's true, that's common, but we're enabling anonymous authentication, that should not be common.
At least anymore.
And we're telling the authorization mode to be always allow. And last, we're running this on 443, but we're running it on the non-TLS port. So this helps getting around some of the firewall restrictions.
443 is unlikely to be blocked by any firewalls and might look like normal traffic.
So we're just going to kube control apply this into our demo cluster again. So now to test this, we can run a pod inside the cluster. And one of my personal favorite containers to run is one by a friend of ours, Rory, called Alpine NetTools.
Greets to Rory McCune.
Okay. So now, we can run curl from inside this attack pod against port 443 of our shadow API server, not the real one, ours. And that's the web request for all secrets in all namespaces for the entire cluster straight out of etcd. And there you go. We've just bypassed the main API server and used ours directly into the database.
And now we have all the secrets, and the logs won't see it because we aren't communicating with the regular API server at all.
Okay. There we go.
So that was pretty cool, but it's not quite a persistence strategy. Let's broaden our horizons a bit. I think we could go bigger. What if we deployed a C2? No, not like spinning up our command and control infrastructure on Kubernetes. We know how to do Kubernetes. That's easy. What if we could build a C2 out of Kubernetes itself? We could call it, C2 Kubernetes. If we have cluster admin, we can do all kinds of cool things in the cluster. We can exfiltrate any data, disrupt any workload, pivot to the nearby environment, and more. So what if, the moment we got cluster admin, we deployed a tailored and sophisticated persistence mechanism very quickly, with the least amount of logs tracking that activity, and the greatest chance of going undetected for the longest period of time? What if we installed an agent on all cluster nodes that joined them to an external cluster that we control? They'd still be a part of their own cluster, and they'd otherwise behave normally. They would just happen to also be a part of our cluster too. That would mean, as attackers, we'd be using Kubernetes as our C2 to control multiple compromised clusters in a single place, while staying lurking in the shadows without being seen. How could we do this?
We could build it using Kubernetes itself, specifically K3s.
What is K3s, and why did we pick K3s to deploy our C2 with? K3s is a smaller, simpler Kubernetes distribution, slightly different than the regular one. It's designed to be lightweight for resource-constrained environments, such as IoT, and its requirements reflect that.
K3s has a different networking requirement than Kubernetes, which are advantageous to us for the purposes of our C2. Most importantly, it only requires a single TLS connection outbound from the nodes to the control plane, which is very likely to be available, and it also blends in with a lot of other valid TLS traffic. K3s has nearly all the same moving parts as the full version of Kubernetes. On the right is a simplified visual of the K3s control plane components in green and the K3s nodes in red. And we'll overlay those on the next slides.
So how could we use K3s to build a C2? We could install the control plane component on a VM we control in another cloud, listening on TCP 443. Again, a relatively common port that's unlikely to be blocked by firewalls. So now that we have elevated access to the target Kubernetes cluster via that control plane, we can deploy a workload that is crafted to escape the container to the underlying host. From there, we can run the K3s node with a configuration to phone home to the control plane on TCP 443 and exit after completing its objective of establishing persistence. The end result looks like this.
Because we've configured our K3s agents running on all the cluster nodes to mount the node's root file system, we have access to all the underlying data on the target nodes. But the original cluster continues to function fully operationally normally. The next time the administrators will run kube-control get pods, they won't see any evidence of K3s running in their nodes, and they won't see the logs of us hitting their API server. And now, we can run daemon sets that continuously run on all these nodes and exfiltrate the data back to us.
So let's demonstrate.
We're now on our attacker-owned K3s control plane on another cloud virtual machine. And I want to show you what this cluster looks like to start. So we're going to get the nodes, and we could see it only has the control plane node. There's no worker nodes in our C2 environment yet. We also have a GKE cluster that we've freshly compromised that has 3 nodes. And we want to show you what that cluster looks like. So this is from the perspective of an admin right now of that GKE cluster. They see their nodes, all 3 of them, everything looks good, right? And you can tell it's GKE because it has GKE in the host names. So we talked about that specifically crafted daemon set. Let's look at it. A daemon set is a special deployment that runs 1 per node only. And in this, what we're doing is we're specifying the BusyBox image. That's a small image with just enough tools. And then we're creating a separate Docker network if necessary. And lastly, we're running a Docker run to install our K3s agent on that node with specific access to the host file system. This then is configured to phone home and automatically join our cluster.
A little bit below, we are using HostPath as a volume mount, which allows us to mount the host file system. HostPath is incredibly dangerous and incredibly powerful, and it allows us to do shenanigans like this. Duffy Cooley and I did a Black Hat talk about it last year, which is on YouTube if you ever want to watch it and learn more.
And one other thing, we add some tolerations to make sure that the Kubernetes scheduler can schedule us on all the nodes down there at the bottom. That's sort of a blanket approach of let us run everywhere. So let's go ahead and deploy our C2 to the GKE cluster. There. I want to show you that for a few seconds up here at the top, I apologize for the wrap, but you can see C2, C2, C2. That's 1 per each of the 3 nodes.
We named it that to make it obvious looking, but it could be named anything that looks totally innocuous.
Security, enforcer, anyway. So back on our K3s control plane, we can now see that we have our original node, but we also have the GKE cluster talking to us as well. They're now part of our cluster.
Sweet.
That was quick, right? So not playing favorites, though, we also have a compromised EKS cluster.
EKS is AWS's managed Kubernetes service offering.
There are those 3. So let's apply this exact same process to the EKS cluster. Okay. And not to leave anyone out, we have an AKS cluster that we've also compromised.
That's Azure's managed Kubernetes service offering.
3 AKSs in the node pool. We'll deploy our C2 the exact same way. When creating this, I was very surprised. There was almost no variance. It worked equally across all. So let's go ahead and clean up really quick. I know that was a little bit more than a few seconds, but we could have made it quicker. So now we're removing traces of us being inside of kube control. So after these commands run, you can see there's only 1 left and it's already terminating. So in about 1 second, it's gone. So now there's no evidence in the GKE cluster. Let's do the exact same process to EKS and AKS. Okay, so as of now, it was like we were never there. So back on K3s, we can run kube control get nodes. But this time, we see all 3 clusters, all 3 nodes, talking to our control plane. And again, back on their clusters, the admins are only seeing their 3 nodes, only their pods. They don't know that anything just happened. So Ian was talking about a special daemon set to steal secrets. What if we could steal all the secrets from all the nodes in a very efficient manner? We could use the daemon set approach. One of these pods running on every single one of the 3 clusters nodes that fetches the secrets that are mounted there and sends them back to us quickly and efficiently.
From all 3 clouds.
So let's go ahead and deploy that into our own controlled cluster. Okay? We'll give it about 3 more seconds. Give it time to do its thing. And now all we're doing is tailing the logs of our daemon set. And as you can see, we've got all the secrets again from all the nodes and all the clusters.
Plain text, easily available, and, we can go use them.
So here's another daemon set we want to show you, one that steals the instance metadata credentials from all the nodes.
Because again, cluster isn't always the end goal. We can also get cloud metadata and then use that to go do things in the cloud as well.
In a similar approach, we can use some wget calls to get the instance metadata from AWS and from GCP, and then Azure we can use to get from the host file system. Similar approach, similar efficiency. We can install our own custom daemon set. And again, give it 2 or 3 seconds. We're patient attackers. And as you can see, we've got access tokens from GCP, and that went a little bit quickly. So we did miss AWS and we did miss Azure, but they are there. If I were to rerun that command, it would show you.
And now we're able to move laterally outside of the cluster into the cloud. All 3 clouds.
Okay.
How's that for a multi-cloud strategy?
And hybrid.
As far as we know, no one has ever done anything like this before. We think it's a good example of what cloud-native attacks can look like in the future, from sophisticated attackers who understand Kubernetes at a deep level, know how to use it well, and have the mindset to know how to misuse it well. This future is exciting, and maybe a little scary, and we all have to prepare for it. Because as sure as Kubernetes releases come every 90 days, this future is going to keep coming. So while we're looking into the future, let's take a look at what's coming and what's already here. Here are some upcoming and new Kubernetes features to keep an eye on, and some things about them to look for in your environments. These features can do interesting things individually and together. So first, ephemeral containers and process namespace sharing. Ephemeral containers, early alpha as of Kubernetes 1.16, are designed for debugging and accomplishing things that more security-restricted configurations, such as distroless images, might make it harder for system administrators to do. They allow cluster admins to do things such as execute commands from sidecar containers and run TCP dump inside a pod. This couldn't have been accomplished before easily, if at all. But ephemeral containers will allow you to do that. Ephemeral containers are especially useful when combined with process namespace sharing, stable as of 1.17, which enables processes in a container to be visible to all other containers in that pod. This combination allows for many interesting possibilities for imaginative attackers, which we don't really have time to cover here. But as attackers, we would like to encourage the offensively minded of you out there to use your imagination, because it's pretty cool.
In previous Kubernetes versions, the Kubernetes components were configured largely by files on the file system or by CLI switches. This provided a natural separation of configuration in Kubernetes from configuration of the Kubernetes components. But it can introduce administrative challenges for automating widespread configuration changes. So to help with this, these two can be configured via the Kubernetes API using dynamic configurations. We can use our privileged access to Kubernetes to reconfigure Kubernetes itself and change and weaken its own security posture. The dynamic audit sync configuration can't modify which API actions the audit log, but it does control where those logs go. So we could use this configuration setting to say, send all the Kubernetes audit logs to a web application that we control instead. We could then filter those logs and forward them on to the original destination to conveniently hide only our malicious activities, thus covering our tracks and avoiding detection. The log stream is still intact.
But wait a minute, that's only the first thing on there. You talked about dynamic audit sync, but what could we do with dynamic kubelet configuration? Well, greets to Kerus, who wrote kubelet exploit a very long time ago. Kubelet exploit was one of the first Kubernetes hacks. It was involved in infamous security breaches, and it could easily be exploited in the wild. You used to just be able to find port 10250, which was the port for the kubelet, on Shodan, and just be able to go do whatever in there. And since then, the defaults have improved. So you can't really do it anymore. It doesn't really work. Personally, though, I kind of miss its ease of use.
The kubelet exploit isn't really an exploit. It's just a configuration on the kubelet API that lets you run arbitrary commands inside any pod's container on that node. Pretty powerful.
Historically, it sure has been exploited, though.
It has. The kubelet's default configuration has become more secure over time, so disallowing old attacks that used to work. But now that reconfiguring the kubelet is so easy via the API, let's use that and disable some of the security features on the kubelet API and bring kubelet exploit back.
We're going to demonstrate this for you.
Okay. So we're back in our demo cluster, and we're going to run another attack pod using the same image as before. Very versatile. I think you should look this one up. Okay. So that's running. So now we're going to use the attack pod to hit the kubelet's API directly. And what we want to do here is we want to show you what it looks like when it's properly configured. As you can see, it's a simple curl command. There's no authentication. And we're hitting the running pods API on the kubelet, saying, tell me all the running pods you have. And as you can see, we get an unauthorized right here. That's the correct response. You should see this if you ran this in your own cluster.
At least now it is.
So in order to reconfigure kubelet, it's more efficient to take its existing configuration and tweak it a little bit. So let's go ahead and hit the Kubernetes API itself with a little bit of JQ magic to make this quicker instead of me typing by hand. We're going to output that to a local file on the file system called kubelet config-z kind worker. So now we're going to go ahead and tweak that. Okay. So there's a lot of configuration settings, but the ones we're concerned about are the webhooks. So let's go ahead and disable that. And we want to enable anonymous authentication too. And let's go ahead and get rid of any authorization as well. So we're basically telling Kubernetes to forget about its security policy. Sorry, kubelet. So what we want to do is take this file that we just configured on our file system and store it inside the Kubernetes API. And we're using a config map called myNodeConfig. Okay. As you can see, our changes are now reflected and stored. Okay? So next, we need to tell the node to reference that configuration instead. We can do this with a shortcut using kubectl patch. So we're just putting a little bit of extra configuration in the exact right spot to tell the worker to use that myNodeConfig in the kube system namespace. So now we can look at the new node's configuration and validate that our changes took. Right here. So config source, config map, kubelet config key, mypod. Sorry, myNodeConfig. Okay? So let's go back to our same attack pod that's still running in the cluster.
And we're going to curl that kubelet API directly again with our newly updated config map.
So the first thing we're going to do again is do some enumeration, right? We're going to hit the kubelet API again. This time we're going to say, hit the running pods, and we're going to use JQ to make it a little bit easier for you to read. There we go. So as you can see, these are all the pods and containers that are running on this particular node. And one in particular that we want to go after in this case is the kube proxy. It has a couple things going for it. It's privileged. It runs on every node because it's part of a daemon set. And it's running as root. So if we can execute commands in the kube proxy, we're one step away from owning the entire node. So now that we gathered our information required for the kubelet exploit, we get the namespace, pod name, which is sometimes random generated, and the name of the container, kube proxy.
We can run commands.
And as you can see, that curl command now is hitting the run API, the kube system namespace, the kube proxy pod, and the kube proxy container. And we ran just list the root directory.
And there we are. It's ours now. So that was awesome. And we've seen that what's old can become new again. Increasing complexity and security leads to demands from administrators and developers for more simplicity and for more ease of use. This can lead to opening up new security holes, or, in some cases, reopening old ones. In the future, we can expect this cycle, this wheel, if you will, to continue to turn. What can we do about this? Here are some actions you can take right now and some things that you can look out for going forward.
So when you go back to, because a lot of you are running Kubernetes, when you go back to your organizations, you're probably going to want to configure alerts on critical Kubernetes audit logs, specifically for changes to webhooks, dynamic configuration items, and RBAC permissions. If you aren't reviewing the audit logs, you really should. Who here is? Please tell me. Excellent, don't want to call you out there. Next, review the feature gate settings and ensure you're only using the desired features, and review RBAC policies for correctness.
In the next 3 to 6 months, you should try out new features of upcoming Kubernetes releases in a development environment to develop a plan for how to deal with those future features, and also develop a plan for upgrades. One thing to know about upgrading Kubernetes is that often if you upgrade in place, the newer security features that come along will not come into your cluster if you upgrade in place. They do this on purpose to avoid breaking changes. So if you're running Kubernetes in prod, it's important to have an upgrade plan, because you might not have as many security features in your cluster as you may think. And after that, in the next 6 months, you should implement that plan for future features as the newer versions of Kubernetes become available to you in your environment. Some of the things we've covered here probably won't be available to most folks in this audience for several more months. So you have some time to plan.
But not that much.
And we want to emphasize that it is possible to secure Kubernetes. And it's doable. It's just kind of hard sometimes, but you can do it. We believe in you.
So here are some resources and further reading if you want to learn more about hacking and hardening Kubernetes.
And in conclusion, we want to emphasize to you all, honk the planet.
Thank you very much.
Thank you very much.